Hello, my name is Marco Rodriguez, and today I'm going to present an application of photochemical grid modeling results with the intent to improve screening tools used to identify the locations we should prioritize to assist populations that may be disproportionately affected by ambient air pollution. I want to acknowledge and thank my colleagues in this slide whose contributions have been invaluable to present this material today. I also want to acknowledge the support we have received from Bramble. What is environmental justice? EPA defines environmental justice as both the fair treatment and the meaningful involvement of all people, regardless of race, color, income, with respect to the decisions, regulations, and policies that result from the implementation of environmental laws. Fair treatment means that no one should bear an undue amount of negative environmental consequences as a result of economic activities or government actions or policies. Meaningful involvement means that people have a fair opportunity for participation in the process that leads to decisions that have the potential to affect their environment and health. The American Rescue Plan legislation signed into law by President Biden this past March has provided the Environmental Protection Agency with funding to address two major initiatives: the air quality monitoring and environmental justice initiatives. Each one of these are funded to a total amount of $50 million. The Air Quality Monitoring Initiative will fund air monitoring for 1. A grant competition for nonprofit community-based organizations, 2. Direct awards to air agencies, and 3. Mobile monitoring labs or air sensor loan programs. This makes it truly important that we identify these potentially disadvantaged communities to support future air monitoring efforts. The Environmental Justice Initiative funds programs to assist communities. For instance, $2.8 million have been currently distributed to 14 environmental justice programs for outreach to underserved communities, for house intervention programs to improve air quality, etc. Notice that $720,000 alone are allocated to enhance the development of EJScreen, which is the current environmental justice analysis tool, as well as to support other related resources. The availability of federal funding is one of the many reasons to have reliable and accurate environmental justice screening tools to identify and better support our at-risk communities. EJScreen, the Environmental Justice Mapping and Screening Tool, is a GIS-based tool developed by EPA and combines 11 environmental indicators and 6 demographic indicators displayed in maps and reports. EJScreen provides a single interface that helps explore environmental and demographic issues in a consistent manner, but as EPA acknowledges, it has a series of limitations. It is predecisional, that is, the tool is not designed as the basis for agencies to make determinations, regulations, or policies. It is incomplete because it does not capture all the relevant environmental issues that could affect a community. Sometimes this is the result of lack of enough quality data to be integrated in the tool. It is uncertain. The demographic uncertainty combined with the uncertainty in environmental data means index values are often quite uncertain. EJScreen includes 11 environmental indicators shown in this table, and you will notice that almost all of them are air-related, either directly or indirectly. This clearly presents many opportunities for the air quality modeling community to add value to this screening tool, improve the quality of the underlying data driving tool, provide additional insights to the main drivers for the indicators, provide additional information not currently considered, etc. It also offers an opportunity for our community to collaborate with experts in other fields, epidemiologists, regulators, other air quality scientists. In this presentation, I will focus on the ozone-related indicator, but as we will see, some of the conclusions can be applied to many other indicators in this table. EJScreen relies on the concept of the EJ index to combine demographic and environmental information. The raw EJ index is calculated for each census block group for a given region or nationally, and is the result of the multiplication of each of the variables shown here. The population is obviously the number of people that live on a given census block. The demographic index is defined as the average of the percent minority and the percent low income within each census block. The second variable here is the difference between the demographic index calculated for the target census block group with the demographic index calculated for the US as a whole. The third variable is the value of a given environmental indicator for the target block group. In the case of ozone, the environmental indicator is the ozone concentrations in units of ppb. The raw index values themselves are hard to interpret, and EPA provides the final expression as a population-weighted percentile. Here, we present a case study in which we focused on the ozone EJ index. Our goal was to replace the underlying data in EJScreen with finer resolution Mercurian modeling output and understand how the EJ index for ozone changes compared to the original dataset. There are some clear advantages to this. There is unexpected additional value in existing modeling data for an area. In this case, previous state implementation plan modeling. But really, any existing local or state modeling could be used for this purpose, provided it has demonstrated acceptable model performance. State or area-specific specialty data may have more accurate emissions than older or outdated national data. In addition, for this case study, the state-specific modeling has a 4-kilometer grid, which is higher in spatial resolution than the default 12-kilometer grid data in EJScreen. Use of the state-specific dataset also opens the door for further analysis, since the modeling data has source apportionment information, which could provide critical insights to inform not just where to monitor, but what to monitor. Our proof of concept study used a modeling projection for the year 2023. This dataset only spans the summer months, so that is one reason we concentrated in ozone instead of particulate matter. But PM is a very important driver for health impacts. The modeling output was processed to obtain the highest values on each grid cell for the 8-hour daily maximum. We went ahead and updated the ozone concentrations and recalculated the ozone EJ index following the methodology shown in slide number 6. This proof of concept method demonstrates the ability to leverage existing modeling data to support environmental justice priorities, which provide added value and benefits beyond their original purpose. Although our case study focuses on Colorado, the methodology presented here can be used or expanded depending on data availability in other regions of the country. The following slides show the results we obtained for the ozone EJ index. This slide shows a comparison between the original ozone EJ index as obtained by default from EJScreen on the left. On the right, you see our results with the state-specific 4-kilometer data. The figures show a zoomed-in area around the Denver metro. North is generally at the top of the figures. For those not familiar with Colorado, the Rocky Mountains are located west of the urban corridor, at the left of each figure. As you can see, it is hard to see any significant differences in the index relative to the national default data. I have circled in blue a few of the block groups where percentiles have changed. So why are the differences so small? To understand what's going on, we decided to look in more detail the data being used to generate the index. This slide shows a comparison of ozone concentrations between the original EJScreen data and the state-specific 4-kilometer modeling data. As you can see, the ozone concentrations in the national default screen are very flat compared to the state-specific 4-kilometer data. They also have less spatial structure, and surprisingly, the ozone concentrations are systematically much lower too. One thing to note here is that the census block groups have similar population counts, but different population densities, which you can see on the area of the blocks, which can be very different. For those census block groups with a large spatial area, the current EJScreen may not capture important spatial gradients of environmental indicators within the block. Next, we decided to investigate how the demographic index compares to the ozone index. You can see in this slide there is quite a high spatial correlation between both. We also checked the raw index values and found they increased relative to the original EJScreen dataset. but importantly, they show the same special correlation with the demographic index. Also, expressing the index as percentiles effectively preserves the same ranking irrespective of the ozone inputs, leaving the ozone index mostly unchanged. This slide shows that the demographic index is the main driver of the ozone index, and this has important implications for the users of the screening tool. If EJScreen is not sensitive to changes in air pollution levels, then its results will not change and air quality related mitigation strategies will not show any impacts or changes for those populations disproportionately affected by air pollution. If the results are not truly representative of environmental burdens, then areas that are heavily burdened may not receive the appropriate resources needed for further investigation and mitigation. What are our take-home messages? We found that updating the ozone concentrations with 4 km resolution had only a small effect in the final EJ index expressed as a percentile. The ozone EJ index is in fact most sensitive to the demographic index. This is in part a consequence of the percentile-based approach in which the index is defined. One recommendation is to re-examine the EJScreen methodology to create a tool that is more reflective or better able to capture the minority and low-income population pollutant burdens as necessary for the screening assessments. We recognize that EJScreen is a screening tool. However, it is important that the tool be sensitive to the environmental indicator fields to provide representative information about the relative differences in pollutant burdens across various communities. Finally, we have a few bullets with future work related to this study. First, conduct a thorough sensitivity analysis of all environmental indicators currently included in EJScreen. Second, evaluate the suitability of different metrics for each of the environmental indicators. For example, consider 1-hour ozone maximum concentrations. And finally, consider adapting EJScreen to enable users to select datasets that leverage the full power of existing information, such as modeling with source apportionment results. Thank you for your time, and do not hesitate to contact me if you have any further questions or comments.